everybody. I'm Paula García, and I work as a design engineer in Airbus Crisa. And today I will be talking about the design flow for a specific electronic space equipment. So the first thing I want to introduce is the role of Airbus Crisa in these two GIESEPP MP and DEEP PPU projects. Well, we are in charge of developing the PPU, and in an electric propulsion field, this stands for Power Processing Unit. So the Power Processing Unit is the power management equipment in charge of providing power to the whole system and also of controlling it. So we're getting the power from the platform, from the satellite batteries or solar panels, and we are transforming it into the high voltage required to operate the thruster and other passive elements of the electric propulsion system, such as the fluid control valves. Although power conversion is the main PPU function, we also perform power regulation. So, for example, we have to deal with our different voltages depending on the operation point of the thruster, and we also perform power conditioning by, for example, removing noise from certain bandwidths or ripple of some signals in order to provide a stable behavior. We also read telemetries and provide control signals to operate the thruster, and the PPU also includes safety features such as overcurrent, overvoltage, and overtemperature protections to ensure that the thruster and the spacecraft are protected from any damage in case of failure. So once that you know the equipment we are intended to design, let's take a closer look at our goals. So the main goals of the design flow are we have to accomplish our design taking into account the electrical requirements and also taking into account that we have a schedule and cost restrictions. Obviously, we want to ensure the quality and reliability of our design, and we want to optimize the manufacturability in terms of number of components and type of components. And last but not least, we want to reach the manufacturing kickoff with a minimized risk in order to avoid changes in the subsequent stages. Those goals might seem super general to you for every single electronic device, and that's actually true. So what are our power processing units challenges? Well, our main goal is to produce a high volume of units at a competitive price and without sacrificing our performances and the reliability of our final products. So we have a few challenges here. For example, the high voltage requirements are super demanding in these both projects, and this means added complexity. For instance, our positive high voltage module has to provide up to 1.5 kilovolts to the thruster screen grid. So as you can imagine, when designing, this means adding a lot of restrictions, for example, with PCBs or testing assemblies or validating components. So yeah, this is quite a restrictive requirement. Also, we are working in the new space framework, and this implies using groundbreaking technologies such as the use of commercial off-the-shelf components and gallium nitride semiconductors, for instance. This directly affects reduction in mass and volume of the unit, and also it affects cost reduction. Also related to this cost reduction, we are working on the traditional PPU architecture. Traditionally, the PPU implemented some functions such as the radio frequency generator in additional units, and we are integrating them in our main one, and this way we can reduce unit integration costs. And well, obviously we have to optimize the power efficiency of our power system and reduce the thermal losses. And on top of that, we have to face all those challenges and reach our goals with a bigger conditioning, which is the space environment. So we have to deal with thermal issues. We have to dissipate power in the vacuum of space where convection doesn't take place. We have to deal with radiation and their single level effects and electrical degradation due to the total radiation doses. We have to deal with other issues such as vibration. So as you can see, we're facing quite challenging designs. Let's move on now to the main stages of our electronic design flow. The main stages are these four. You can see them here. They are requirements, then will come the specification and architecture design or preliminary design, and finally our detailed design. And now that you know a bit more about the product we are intended to design and the challenges we're facing, I'd like to raise a question that you will be able to see probably through the WebEx platform. I'm seeing it, so I guess you also can. It's kind of an open question about your opinion on which of the ones answers that I propose you think would be the most suitable to optimize the design flow. So just tell me what you think. I think the quiz has a maximum duration of 5 minutes, so take that into account. And I will be talking about it and commenting the results of it by the end of my presentation. Meanwhile, and yeah, we can already start with the very first phase, which I don't know why my slide won't. Okay, so the very first phases are requirements and specification phases, and this stage is structured around three main principles. First, we have to take into account the market analysis Fabian has been telling us about in the first presentation. Secondly, we have to really know the platform needs and the electric propulsion system needs, which also includes the thruster characteristics that our Ariane Group colleagues have been telling us about in the latest presentation. And thirdly, we have to take into account our internal requirements to be compliant with our own processes. So you can see here some of the outputs of these stages, for example, unit modularity or external interfaces. And this phase is a really collaborative phase in which the first income is a set of requirements set by our clients, but during a co-engineering process where every single part involved with their expertise tries to modify and adapt these requirements in order to be feasible with the final design. So we will come up with a final kind of preliminary requirement assessment, which we call the requirement review, and then we can move on to the next phase, which is the preliminary design phase. So the main objective of this phase is to prove the feasibility of our unit and to identify all the risks. At this point, the design topologies are captured in electrical schematics, and electrical simulations are launched to prove correct functionalities. The outputs, you can see them in this first column. So we should get preliminary budgets as an output. Also, we should define materials and processes. We will develop a preliminary mechanical model, and also sometimes we develop what we call the EVBs or breadboards, which are basically prototypes. I will talk about them a bit later. So to get all these outputs in Crisa, we have developed customized tools. The thing is, in every single stage, we have really specific purposes. So in order to optimize the reliability of the results and the time we spend doing that analysis, we have customized tools in order to get these outputs. So, for example, well, the first thing should be choosing our components. That is a critical step in our design. So we must take into account that the components we choose will have to ensure a reliable performance during the whole mission. So that is why they are submitted to a rigorous test and qualification process. In Crisa, we have a kind of central platform or database that you can see a bit here. And as you can see, here we have information about electrical, electronical, and electromechanical parts, not only passive components. You can see also here connectors or magnetics. So for every single one of the components, we could check here their maximum ratings, for example, or other useful information that is available on the datasheet, but also other data such as radiation test results or lessons learned about particularities of the specific component that we have come across in previous designs. This database is constantly evolving, so we are updating it with new tests or new components. And one of its great advantages is that it's the main data source for all the rest of the tools that we use in Crisa. So this reduces a lot errors and avoids risks. So let me go back to the previous slide, where you can see that budgets are also an important output at this stage. For example, we develop power budgets in which we have to make sure that we can handle the power that we are dissipating and the efficiency that our unit has is okay with the electrical requirements. And also we have to perform the what we call surface budgets, which are basically an estimation of the occupation of our topologies in the mechanical model. So for this particular budget, a tool has also been developed. You can see it here. We call it Blocks Analyzer, and it will automatically read our electrical and electronic schematics and give us super useful data such as the total occupation, the total mass of that module or of that function, and, for example, the maximum height of the highest component. Yeah, in this phase, sometimes when we have functions or topologies that have low maturity or high risk, we develop breadboards. For example, in our positive high voltage module, we developed several breadboards here in this particular phase. Some of them were meant to try and test new topologies and their functionalities, and some others were to try components under conditions that had never been tested before. Sorry. So we do all this to prove that our module is mature enough at this early stage and that it is feasible. So we kind of formalize that through a preliminary design review, and then we can move on to the detailed design. So once we've proved that our solution is feasible and that we have identified and controlled risk, now we have to prove with detailed analysis that we are fully compliant with the electrical requirements. And we do that through this extensive analysis. We perform a lot of analysis in this phase, as you can see here. For example, every single budget that was preliminarily developed in the earlier stage is refined in this one. Also, we perform the failure mode analysis, which basically consists on verifying that possible failures won't propagate outside the PPU to the rest of the system, and that we don't provoke overconsumptions. Also, we develop finite element models in order to provide analysis about radiation, thermal, and mechanical studies. And here you can also see the PSA, which is the part stress analysis. With this analysis, we are trying to demonstrate that every single one of our components on the topologies during this life is working below their maximum ratings. And also we have the worst case analysis, for which we have also developed a customized tool that you can see right here. It would look like this. And the worst case analysis is based on varying the tolerance of the components with a Monte Carlo method. It will take into account the drifts in temperature, aging, and radiation of every single component, and it will try to run a lot of cases to find the worst case scenario. So with this study, we have to prove that throughout the lifetime of the design, we maintain the desired functionality. Also, you have here the reliability analysis in this same line that is intended to verify that the PPU will be compliant with the specified maximum failure rate during this whole operational life. And once we've done all those analyses and that we have provided evidence of compliance for the requirements, then at this point the design is validated and its process is closed. Well, we can start with the kickoff of our very first model. At this point, we have 3 standards. We have electrical models, qualification models, and flight models. So the first 2 stand for system performance and system qualification, and the flight model is the one that will be launched. So let's take a closer look at the next steps for the flight module. So following the design, the next stages for this flight module would be unit qualifications. Once every module has been integrated, then we should have the flight unit acceptance, and here is where our work stands, and our customers will perform the subsequent stages, which are the system integration into the satellite, and finally the launch. And now that you know a bit more about our design process, I'd like to take a look at your answers on the poll we previously launched. I'm sure we could talk about this debate for another 20 minutes, but as we don't have that time, I'll just go a bit through them and tell you what I think. I see that you're the prototypers. And okay, so to me, there's no wrong answer here. I'm sure that you would have chosen more than one of the answers. And actually, in Crisa, we are already developing more than one of those answers. So, firstly, to me, it's obvious that we have to be evaluating and testing new enhanced components. There are tendencies that seem really promising, such as the gallium nitride semiconductors that we are already using in these projects and in many others. And yeah, surely we have to keep an eye on that if we want to keep developing competitive products. With the next 2, with the prototyping and analysis, I feel like there's always that kind of struggle of when to prioritize analysis over prototyping. But the truth is that prototyping everything from the very first beginning of the design stages is not feasible, because we have limited resources, and we would consume many of them if we had to design the prototype, manufacture the prototype, and then test the prototype. So this is why we have to carefully choose, as we do with the breadboards, and based in engineering criteria, what we do prototype and what we do not prototype. So what is truly in our hands is enhancing the power of our analysis and the reliability of the results and the time we spend making those. So that is why we develop our own custom tools. There's a long way, I think, to explore regarding computational power of analysis, and maybe even adapting to these new trends like artificial intelligence trends, and maybe not only in our analysis, but also in the manufacturing process. So in any case, as a conclusion, what is pretty clear is that we have a huge conditioning in our sector that makes us extensively prove the reliability of our design, which is the space environment and the long duration of the missions. So our key to that is obviously our consolidated knowledge, but also keeping up with these new trends and tendencies, evolving and taking improvements in the process to keep developing the most suitable space equipment solutions, such as this power processing unit. And that brings me to the end of my presentation, if I can say that. Okay, yeah, this brings me to the end of the presentation. Thank you very much for listening, and if you have any questions, I gladly try to answer them to the question and answer section.